Hello, my name is Jed Murdoch. Welcome to Module 9 on inbreeding and outbreeding. In this module, we'll cover the basics of inbreeding and outbreeding, what those two things really are, what they mean, how they affect a population from a genetic point of view, and we'll also look at some ways by which you can quantify or estimate the amount of inbreeding or outbreeding occurring in a population. So I'll say a few notes at the beginning to introduce these concepts. My colleague here, Terry, will come in and build a spreadsheet that will demonstrate much of what we've covered a little bit later on. Before we begin, let me recommend that you review the module on the Hardy-Weinberg principle. That module covers some basic genetic terms, things like genes and alleles. It will also cover things like the term heterozygous, homozygous, heterozygosity, homozygosity, and that sort of thing that I think are quite valuable to understanding this module. It'll also cover the Hardy-Weinberg principle, which we'll revisit a few times throughout the course of this module. So let's begin. Consider genetic diversity. Genetic diversity, it's a big term. Conservation biologists are oftentimes concerned with maintaining relatively high levels of genetic diversity within populations. Why is that? Well, I guess the prevailing notion is that the higher amount of diversity among the genetic makeup of a population allows that population then to respond or to be more resilient to changes that we might see in the future. So the world is a bit unpredictable and a bit changing, and the more diversity there is in the genetic makeup of that population then, the greater the ability or the capacity to respond to those changes, to adapt, to evolve. So genetic diversity in that sense might be considered an insurance policy against change in the future. We also see that high levels of genetic diversity can have positive influences on individuals, although this isn't always the case, but certainly in some species, in some circumstances, we've seen higher amounts of genetic diversity increasing fitness. And I don't mean fitness in the sort of physical fitness Charles Atlas way, I mean fitness in the sense of the biological. So fitness being survival and reproductive output. So we have seen in some species greater amounts of fitness and reproductive output when there's higher diversity. But again, as a caveat, even though that's a conventional notion, that's not always the case. So in the modern world, humans have quite an impact on the landscape, right? We have the capacity to change landscapes greatly. We tend to take large areas that may be continuous and carve them up and fragment them into pieces. And that can have effects on populations. If we have a continuous population that gets smaller and smaller and smaller and more islandized, one effect that we've seen is that that can result in lower amounts of genetic diversity within the population. And so one of the questions is, what sort of processes cause that lower diversity? And one of those, which we've covered in another module, is through the random process of genetic drift. So genetic drift can affect allele frequencies. It can cause, through a random process, some alleles to become fixed in populations and other alleles to be expunged or to be lost from those populations. And that can lead to lower amounts of diversity. Another consequence here, or another cause I should say, is that it results in higher amounts of inbreeding. So as populations become smaller and smaller and more separated from the rest of a broader population, the opportunities for randomly mating with others out there becomes lower and lower, and that results in inbreeding. And that's a term you've probably heard in a variety of different contexts. Inbreeding. What does it mean in sort of a biological sense? It occurs when mated pairs come together and share genotypes that are much more similar than what you'd expect if random mating occurred. So their genotypes, when they're coming together, are much more similar than what you might expect based on Hardy-Weinberg, for example, which assumes random mating. So inbreeding has a consequence specifically in terms of genetics. What it tends to do is result in decreased amounts of heterozygosity in the population because you have individuals with similar genotypes probably sharing similar genes, alleles rather, and passing those on to offspring, and that results in greater amounts of homozygosity. So reductions in heterozygosity occurs due to inbreeding. Sometimes that has a negative consequence to fitness. We've certainly seen this, and when that happens, we refer to this situation as inbreeding depression. So inbreeding depression results in lower, decreased amounts of fitness as a result of inbreeding. And certainly we've seen that in captive populations, right? So envision a zoo. Zoos oftentimes are involved in breeding individuals to establish larger populations for reintroduction, eventually to safeguard perhaps against extinction in the wild. And so there is a fair amount of inbreeding that can occur among captive populations, and we've seen in some circumstances that result in offspring then that have diminished reproductive output. So I will say that zoos do spend quite a bit of energy trying to maximize genetic diversity and reduce the amount of potential inbreeding. So that's inbreeding depression. We have seen it in some wild populations as well, although there are not a tremendous number of documented cases. So we have seen it in song sparrows, we've seen it in land snails. For the mammal people, we've seen it in white-footed mice, and we've also seen it in a magnificent species called the Glanville fritillary butterfly. The Glanville fritillary butterfly is fairly well known, partly because it served as a model species for understanding the basics of the metapopulation concept. So much of the science behind metapopulations has come from studies of these butterflies, mainly in Finland and parts of Europe. We do have a module on metapopulations I'd recommend you view if you're interested in that subject. So we also have the flip side of inbreeding occurring. So this is another form of non-random mating. And outbreeding, as it's referred to, is a situation in which you have individuals coming together in mating that have genotypes that are less similar than what you'd expect if they had mated at random. So the genotypes are similar than random mating. And you might think at first blush, well, that's probably a good thing. It probably results in greater amounts of diversity because these individuals are much less similar than what you'd expect if they had mated randomly among the population. And we certainly have seen that in some species. So outbreeding among crop plants, for example, can produce higher yields. But there can be negative consequences to the fitness of individuals as well when outbreeding occurs. And when that happens, not surprisingly, we refer to that situation as being outbreeding depression. So let's have a quick look at an example.
So imagine two populations now, two populations of any species, let's say red foxes. We have a population here on the left that may be occupying some forested region, and then we've got another population, a separate population on the right, that's occupying another forested area. So the foxes in population 1 carry the genotype AA. And AA, those foxes, are best suited or best locally adapted to the conditions here in this particular landscape, in this region. On this side, we have foxes that carry the genotype BB, and they are best suited or most locally adapted to those conditions in this particular region, in this forested area. So from a fitness perspective now, on this side, we have those carrying AA having greater fitness than those with BB, and greater fitness than those that are heterozygotes, those that are AB. And similarly, on this side, from a fitness perspective, we have those with BB having greater fitness than those that are AA and the heterozygotes, the ABs. So, to look at the effect of outbreeding, let's imagine that we've connected these two landscapes, these two areas, by some sort of corridor. So we've connected them in some fashion. And when we connect them, what we see is that individuals from this population now are allowed to mix with those from this population. And those from this side are now mixing with individuals from this side. So we have allowed these individuals to mix, to mingle, and to start breeding. And what happens from a genetic perspective? Well, we have offspring now that are created that have the AB form. We've created heterozygotes. So by virtue of connecting this landscape, we have increased the amount of heterozygosity in this whole population. But what's the problem here? The problem is that AB is not particularly well adapted to this population or this area, and it's not particularly well adapted to this population over here or this area. So from an overall population perspective, now that we have connected these two areas, what we see is that there now is a depressive effect on the fitness of this whole population. So we've increased heterozygosity, but in this circumstance, it has not been very good from an overall fitness perspective. And this might be of concern to you if you're a conservation biologist and you are perhaps considering connecting two areas or two landscapes with some form of corridor, which is a popular technique in landscape management.
So we have two forms of non-random mating. We have inbreeding and we have outbreeding. And in this module, we'll look at how inbreeding and outbreeding affect things like genotype frequencies and allele frequencies. So remember, inbreeding now results in lower amounts of heterozygosity in a population, whereas outbreeding, the flip side here, results in higher amounts of heterozygosity within that population. So one question that oftentimes comes up is, how do you estimate or quantify the relative amount of inbreeding or outbreeding, this non-random mating occurring? How do you quantify the level of inbreeding or outbreeding? Seems like a reasonable question. One common approach is to estimate how much heterozygosity we would expect in a population based on a scenario in which there is random mating. And if you recall, that sort of situation could be estimated by using the Hardy-Weinberg principle. So when a population is in equilibrium, when it's in Hardy-Weinberg equilibrium, we're assuming that mating is random. And we're not only assuming that, we're assuming that there's no mutation, migration, or sort of natural selection occurring on that population. So if we can estimate what we expect by Hardy-Weinberg, what we expect at equilibrium with respect to the amount of heterozygosity in the population, we then would compare that to what we might observe in a population. So that population may be exhibiting some form of non-random mating, so we're making comparisons between what we'd expect in a random scenario versus what we actually observe. Make sense? Let's look at an example. Let's look at one of my favorites, the kit fox. The kit fox is an arid-adapted desert species that really lives in the western United States and northern Mexico, basically from about the Rocky Mountains onward to the west. They're a nocturnal species, so many of you probably haven't seen them, but they're really, I think, an iconic species of North America. We know that kit foxes are threatened in some areas. So there's a subspecies called the San Joaquin kit fox that lives in the Central Valley of California that's not doing so well. And we know that the kit foxes there live in the small remaining parcels of undeveloped land there, and they also happen to live in the city of Bakersfield, which has 300,000 plus residents. So they have managed to adapt to an urban environment to some extent. But let's consider this kit fox population and first estimate what we expect the genotype frequencies to be like in a population that's in Hardy-Weinberg. So let's consider a single gene in our kit fox population, and let's say there are two forms of it, allele number 1 and allele number 2. And if you recall from the Hardy-Weinberg principle module, there is some convention here. We oftentimes refer to the frequencies of alleles by some letters. So the frequency of the A1 allele we oftentimes refer to as being P, and the frequency of the A2 allele, the second form here, we would refer to as being Q. And remember that P plus Q, or the frequency of all the alleles that might be contained in a particular gene, must add up to the value 1. So if we know allele frequencies, we can estimate genotype frequencies in Hardy-Weinberg. So let's say that we have the P, or the frequency of the A1 allele, being 0.6 in our population. And let's say the Q, or the frequency of the A2 here, being 0.4. If we know these values, then we can use Hardy-Weinberg to estimate genotype frequencies. So let's go ahead and do that just now. Remember that Hardy-Weinberg predicts genotypes at equilibrium, and it predicts it using the equation p squared plus 2pq plus q squared equals 1. So the terms in this equation now represent our three primary genotype frequencies. So p squared here represents our A1 genotype, and our 2pq here represents our heterozygotes, so our A1, A2s, and the q squared term represents our other homozygotes, our A2, A2s. So these three frequencies should add up to 1. So let's calculate the genotype frequencies now for our three primary genotypes in our kit fox population. And remember that P, in this case, the frequency of our A1 allele, is 0.6, and Q, the frequency of our A2 allele here, is 0.4. In this case, if we want to estimate the frequency of A1, we would do that by simply multiplying P, which is 0.6 times 0.6, or 0.6 squared, which gives us 0.36. So 36% of our population we would expect to carry this genotype, A1, they're homozygous. For our heterozygous population, what would we expect in terms of genotype frequencies? Well, we simply multiply 2 times what we know to be the P frequency, 0.6, times 0.4, which is our Q frequency, and that should give us, if I've done the math correctly, 0.48. So 48% of our population now should be carriers of this genotype in a Hardy-Weinberg state, so a population that's in Hardy-Weinberg. And then finally, for our final genotype, our A2 genotype, we simply multiply our Q frequency, our A2 frequency, times our A2 frequency, or 0.4 squared. And that gives us 0.16. So we would expect now that 16% of our population to be carrying the A2 genotype. So all of these three here should, of course, add to 1.36.48, and 16, which I believe, if I've done the math correctly, does in fact occur. A key point here is that when we're dealing with inbreeding and outbreeding, we're really interested in the amount of heterozygosity. So in this case, 48% is really key in understanding what we'd expect in a population that's in this Hardy-Weinberg equilibrium to be with respect to genotypes. We expect 48% to be heterozygous A1, A2.